All right, everybody. Welcome to our second lecture. Thanks for bearing with me of doing a recorded lecture. Hope you guys got to enjoy all the sleeping time. You can tell my voice is still not good, but I'm going to have to push through because I don't want to give this lecture to you all too late and you have less time to do the homework because there's a quiz coming up on Monday, right? Let's see, some water will make it better. All right. I'll try my best, but if there's any questions, if you can't understand me too well, just let me know. Okay, here we go. All right, so we're going to go over chapter 2 today. This is lecture 2, January 7th. And I am planning on, I'll send an announcement, but planning on also getting a head start in chapter 3. I'm going to make another recording for that. Hopefully my voice is a little bit better by then. Okay, so for the agenda today, we're going to talk about chapter 2, fluid statics, and this consists of pressure at a specific point, which I'll just talk about concept-wise, pressure variation in a fluid at rest, and this is really important for a lot of the equations we're going to use throughout the other problems. Incompressible fluid, which basically just means the density is not changing with the water. We have some manometry problems, which is basically using tubes, and you'll see with different fluids, and they'll have different specific gravities and densities and whatnot. Then we can calculate fluid heights and pressures that way. And then we're going to talk about hydrostatic forces on a plane. It's basically a plate you'll see submerged underwater, and we're going to be applying some forces, or the forces and the pressure is going to be coming from the fluid. And we're going to see how to analyze those in equations we're going to use for problems. And then towards the end, we're going to have a quick info about a quiz for Monday for January 12th. I will also make an announcement post as well about this. And I didn't get to talk about office hours last lecture, so I'll have a little bit to talk about for that. All right, let's get into it. This is exciting because now we're going to talk about fluid statics. Right, previously in chapter 1, we really just talked about a bunch of fluid properties and things such as specific weights, density, right? And now we actually get to do some calculation and application for some problems that we're going to go through today. So for statics, right, fluid statics, sorry if I said statistics earlier, it's statics. Fluid is at rest, just like your normal statics class. We're basically assuming the molecules have no motion, right, and the fluid is at rest there. And the big thing about this is that we can assume that there is no shear stress, right? Because shear stress is really what's making the fluid move. You'll see later on. So we can assume there's no shear stress, so we won't have to use any shear stress equations for our calculations today. You'll see it's mainly just going to be based off of the specific weight of liquids and gravity. Oh, and then that leads me to my next point, right? It's just going to be pressures and gravity. And for this case, for fluid statics, pressure is just force. Let's see if I can get a laser pointer here. Pressure is just a force applied to the perpendicular fluid element. And I'm going to show an example here soon of what I mean by that. But basically, it's just right, your normal mechanics of materials. It's just your force applied to the perpendicular area. And just like I said here before, we're assuming zero shear stress if fluid moves as a rigid body. This only works for fluid statics. And I guess, like I said, we already have homework solutions, but if you were to do your given finds and assumes, these are some assumptions that you could write down. Okay, so our first topic we're going to talk about is pressure at a point. And there is, let's see if I can hide this guy. Okay, there was a pop-up, sorry. So this is just kind of a concept thing and right here is what I really want you to understand what it's for. The whole goal is to show you how for a pressure at a specific point that we want, the direction does not really matter. So I'm going to go just talk you through this just so you can see why this is important. So for simplicity, we're going to ignore the x direction, right? So that's kind of the direction coming towards us, and allow the fluid element to have acceleration. Even though we're interested for the fluid at rest, it's just easier to solve because we'll have something that fully equal to 0 here. And you'll see here in the calculations why we do this. So here we have this figure, I guess they're calling it 2.1. It's a forces on an arbitrary wedge-shaped fluid, element of a fluid. So this is just an element of a fluid. And you can see here, if you see this triangle here, there's a term for it, it's going to show up later, but it just basically means the top of the water. I think, we'll see it later. It's called surface free or something like that, but this triangle just means the surface of the water. So here you can just see all these 4 arrows, right? 1, 2, 3, 4. These are the forces applied to this wedge-shaped element of a fluid. And if you do dimensional analysis, like I always say, I'm a big fan of units. Pressure times, this is delta x, delta z. That's just the change in the x direction and change in the z direction. Right, so x direction and then z direction. So let's say we're at SI units, newtons over meter squared. This is meter times meter, right? Your units just come out to be newtons. So that's a force. Same thing here. You can do dimensional analysis for your specific gravity, right? And you basically have your newtons over volume. And then the volume here cancels out with these 3. And you can see here for this force right here, for the gravity exerted for the wedge-shaped element of a fluid, we are using this specific gravity that's pointing downwards, right? And we're using divided by 2 because I believe they're assuming this is in the middle of the wedge. So it's just all these delta x, delta y, delta z divided by 2. Here's pressure on the face of the wedge. You'll have this angle here, right? So they have PS here, a change in x, and then change in s here, or delta s. And then you have your pressure in the z here. So that's all the forces acting on the wedge. Hopefully that is clear. And before we even dive into the summation of forces, just look at these. Oh, let me get my pointer back here. Just look at these 2 equations that I have up here. This is just for geometry, and we're going to plug these in for simplification. So delta y, you can just see here, right? This change in y is equal to delta s cosine theta, right? So let's see, delta y is right here, right? Delta s is right here. So the adjacent over hypotenuse, that's the same as saying delta y. You can do the same thing here with same exercise with delta z. Okay, so we just have these in our back pocket, and I'm going to show you where we're going to use them. So now we're going to do the summations of forces in the y direction, which is going left and right on the screen, and then summation of forces in the z direction, going vertically up and down. Okay, so right, we start off with our pressure y, which comes from here, goes to the right. We add that, and subtract our pressure s, and here we are going to take the sine theta, because if we have this here, we do the sine, so opposite over hypotenuse, and that's going in the other direction, right? So that's subtracting, and then we equal this to the equals ma, and here is our a, right? And we have this so it doesn't equal 0. Like I said, you can use your dimensional analysis. This row, right, is kilograms over meters cubed. This will cancel out meters, meters, meters. So meters cubed, and then this is just going to be kilogram, and then so it's going to be kilogram times acceleration, so m times a. Same thing in the z direction here. We have your pz, which is going upwards there, and then we have our ps, which is going downwards, and then we have our gravity of, or the actual specific weight here of our fluid element. And then it equals the same on the right-hand side that he's previously explained, but this time in the z direction. And now you can substitute this delta y and delta z into these 2 equations, wherever you see them. And you're going to see it's going to simplify to these 2 equations down here. So P pressure in the y direction minus pressure in the s. So PYPS is equals to the density times acceleration, and then change in y divided by 2. Here's the other equation down here, right? So pressure in the z minus pressure in s is equal to density of the acceleration plus specific weight times the delta z divided by 2. And this is just factored out here. I believe you guys should be able to do this algebra. If there's any trouble, let me know, but I think you guys should be able to do that. So now we're going to take the limit as delta x, y, and z goes to 0. And the reason is for that is because we're interested in a point, right? So once it reaches to 0, we're at that point, and we're going to maintain the angularity of whatever these forces are applied at, right? So now if you have this equals 0, this equals 0, you basically get all these pressures in different directions all equaling each other. So this means pressure at a point for a fluid at rest or in motion, which is because we had acceleration here, is independent of direction if there is no shear stress present. You know, I don't want to confuse you guys. I'm just going to take out this in motion here. I'll write that in the updated slides. We'll just say this means pressure at a point for a fluid at rest is independent. Okay. I might have to change that here too. I'm just making it clear here. Why is this important? It's because since we will be calculating pressures at a specific point for fluids at rest, and we do not account for direction. And you'll see that in the example problems that we're going to go through. Let's see if, sorry. Panopto is saying we're in for 12 minutes. We're doing okay. I'm actually going to do a timer on my phone too then. That way I can kind of see. Okay, so pressure variation in a fluid at rest is a section 2.3. So this equation right here that I have is from section 2.2. Just because I want to save time and I might need to do, like I said, a chapter 3 introduction, we're just going to get this equation from section 2.2. If you want to see the derivation, there's a lot of gradient and partial derivatives, and it's basically applying just the surface forces, I believe, and forces applied to a specific element. So, but it basically sums into this, the gradient of the pressures, right? Plus the specific weight in the k or z direction, right? K is unit vector, equaling to 0. And right, the gradient from your multivariable calculus class, right? That basically just means to take the partial derivative with respect to that direction, right? In all three directions. So in short, right, once you, the equation comes, like I said, like it comes from the surface forces and body forces. That's where this equation comes from. Acting on a small fluid and saying the acceleration equal to 0, your x and y is equal to 0, and your z direction, if you take, I guess, the partial derivative with respect to z, you get, because you're adding this term to the other side, or sorry, you're subtracting this term to the other side, right? You're stuck with this equation here. And let's talk about what this equation means, because, right, this just means how the pressure is changing with respect to the z direction is related to the specific weight. And you'll see here, right, that just conceptually, right, you just know, like in water, as you go deeper down into the water, the pressure increases, right? So pressure varies with height. And I'll have some examples of that here in my next slide. Oh, here we are. So pressure decreases as the z direction increases. Okay. I should say increases in the down. Yeah. So I guess it depends, right? Like in water, it increases in the downward direction, but for the sake of this graph, as z increases, the pressure decreases. So I'll just keep that in the slides. I don't think that's too confusing. So right here is your specific weight here affecting your slope. And then here's the equation that we had, right? Change in pressure with respect to z is equal to your negative specific weight because the slope's going down, right? That's the negative. And here are some examples that you'll kind of have in your everyday life you can kind of think of, right? So higher altitudes, kind of like how I'm in Colorado right now, they have lower pressure. So with the lower pressure, right, sometimes it affects your hikes, or it's harder to breathe when you're in higher elevation because of the decrease in pressure. And in planes and in any aircraft, right, the pressure is a lot lower in higher altitudes. And the way you can think about this, right, is because I don't know if you've seen in movies when like a door blows out on a plane, right? All the air is getting sucked out of the plane. So pressure always goes from a higher pressure to a lower pressure, and it's the pressure inside the cabin of where you sit is higher because for your comfort. And I know this because I work for Boeing, and you're more comfortable inside the plane, so the pressure is higher. They pressurize it, and let's say if that door opens up or there's a hole in the fuselage, the body of the plane, all that air is going out because and there's like a vacuum sucking everything from the inside of the plane because of the lower pressure. And I thought that was kind of interesting, right? Because that just kind of shows our equation here of the pressure gets lower with a greater z, or higher altitude in this example. And if you ever happen to forget this equation, right, a good way of just remembering it is as you go deeper in the water, the pressures increase. And you kind of just know that, right? Because like for submarines, they account for pressurization with deeper depths. For divers, they have to also, watch out for the deeper pressures and deeper depths. And I'm not a diver, so I can't talk too much about it, but I know they have to account for that somehow, right? Sorry, guys. Let me get a drink of water. Okay. Incompressible fluids. So assume incompressible fluid assumption. So this is another assumption that you could make when you're doing static problems for fluids. So this essentially just means constant density. So your fluid is not really changing its density, right? And it means also constant specific weight, because if you remember, specific weight and density are related, right? And so so something to note, you can just have this on the side if you want to assume incompressible fluids for problems. Hydrostatic distribution, this just means pressure varies linearly with depth, which we kind of talked about, but we'll talk more in later slides about this. The term pressure head, you'll hear that in some problems, and that essentially means the height of a column of a fluid required to give the pressure difference. So that's basically this P2 minus P1 in this diagram. And here it is, right? The free surface I was talking about, pressure initial here on the free surface. They're just showing this Z2 is a distance in the Z direction. There's Z1, and you can see as you go deeper, right, or lower there, the pressure increases. So you come up with this equation here that you want to note, that the pressure is equal to the height times the specific weight. And as the height is increasing downwards, you get more pressure, and you add up the initial pressure here from the free surface. And this is important. This is something you probably want to have in your equation sheet. Okay, manometry. Okay, manometry is it's essentially a measuring technique that uses heights of different fluids in tubes to find pressures, specific weights, and other heights of fluids. So here we're going to go through this example, but usually you have two different kinds of fluids. So you have your point A here, right? And then you have this blue fluid, which is shows here by the specific weight, this gamma 1. And then you have gamma 2, a second fluid, and you have these heights, and it's open here on the atmosphere. And we're going to go through how this works. But here on the right, I found a picture online in a YouTube video of like a high school experiment. So you see there is a tube here that connects up here, and this just connects to a U-tube because it's a U shape. And you can see as this gets lower, this tool, as the pressure increases, this pressure gets pushed down here and increases the height over here. And that's how you can calculate, your densities and specific weights of different fluids. So let's get right into it. So manometry continued. Here are the key equations for manometer calculations. This is kind of what you had already before, right? So the pressure is equal to the specific weight times the height. And you can also use the pressure is equal to the, I guess this is actually kind of contradicting each other because, this P doesn't equal this P. I'm just saying, you'll see what I mean. Once you are solving these problems, you might have to add one side or this P naught to one side or not. So I guess, sorry, let's just fix that now. I don't want to contradict myself in my slides here. Let's take this out and just leave this, like this equation. Worst case, this P naught is equal to 0. Okay, so P is pressure, specific weight, right? Density times gravity, and then initial pressure. So how do you do these problems? This is kind of how I summarized it. I think a textbook has a kind of different wording, but I think this kind of made a bit more sense. It varies per situation. But so first step is you want to find the given pressure. You usually can set this as your P naught at either end of the manometer. So that could mean the first end is here, this point A, or this open atmospheric end. You'll see in the example here, I'm going to work left to right. You could also work from right to left. So here, so you see my 2 bullet points here. Could be end of manometer open to atmosphere, or it could be end of manometer in a volume with a certain fluid. So here's the big part. As you're working through the manometer, you're going to add your pressures, right? Because the pressure is equal to the gamma, the specific weight times the height. If the height is increasing, right, you're going to add it. If the height is decreasing, you're going to subtract it. And the way you can think about this is if you're going lower in depth, right, the pressure is increasing. Like I always say, if you're going down lower into water, pressure is increasing, so you should add it. But if you're going higher in your water, if you're like swimming, pressure is decreasing, you subtract it. Oh, so sorry, everybody. I'm just not feeling too well, but we got to keep this class going. So, all right. So after you add and subtract as many fluids as you need, you set the expression equal to the other end of the manometer. And that could be whichever end you're left with. So the same as these 2 bullet points. Key tip, I recommend you work from one end to the other end of the manometer, right? I wouldn't go one end to the other and then work in the middle for some reason, right? Work kind of systematically to reduce your errors. Okay, let's jump right into it. So let's create an expression for the U-tube manometer that we were looking at. So we're going to start from the left here, from this point A. You can see this point A is on the same level as this point 1. So we can say that these pressures are the same because it's the same fluid and same height. So we're just going to call it PA, I guess. And we're going to develop the left-hand side of our equation for fluid 1, which is here. So here we have our pressure A, which is pressure A here. And you can see we're going down our manometer tube, right? And as we go down the manometer tube, pressure is increasing. So we add because pressure is increasing, right? So you add plus gamma times H, which is specific weight times the height. Okay, and then we work around the manometer here. So from this point here, this 2 to this 3, this is technically the same pressure because the height is the same and the fluid is also the same. So you can kind of just jump over here already. So now we just have to account for this now. So we're now increasing, we're getting higher in height, right? So like I said, the analogy I always use with water, since you're going higher, right, in height, the pressure is decreasing. So you're going to subtract gamma 2 times H2. And now you set the expression equal to the open end, which is the pressure atmospheric here I have. So you set this whole expression equal to the pressure atmospheric, which is the open end here. And if you look at the textbook, they do a little differently. I thought this was a lot easier, right? You just start from left to right and set it equal to what you end off with. And in the textbook, it's not the exact same way they have it, but they just have it rearranged in different ways. So this is still equivalent to what the textbook has. Okay, we're going to do another example. This time there is values. I'm sorry that I don't have like a whiteboard or anything. I thought of doing pencil paper, and I don't know how good the quality would be. So I was just gonna kind of do it on the screen here and talk you through it. But when we're in person in classes and we have these, I'm going to do it on the board so we can kind of solve them together. Maybe it's a little bit a nicer presentation for you. Okay, so here we have a closed tank. You can see that contains air, oil. We have the specific gravity of oil. And then we have the U-tube manometer here. We have the specific gravity of mercury, noted as subscript Hg. And is connected in the tank as shown here. And the column heights are H1, which is that height, 36 inches, H2, 6 inches, H3, 9 inches. Determine the pressure reading in PSI of the gauge, right? We talked about absolute pressure and gauge pressure, right? And that was in chapter 1. Okay, let's get right into it. And this is pretty similar to the previous example we did with just variables, but now we're putting in values. So, like I said in my steps, right, let's start left to right. So we start with the air pressure. So we're going to start off with P air here. Okay, so now since we're changing fluids, we are now going to account for that. So you can see we're getting lower in depth. So as depth increases here, we're going to have the pressure increase. We're going down and the pressure increases. So to get to right before we get mercury, you have H1 and H2. So we add these two heights, and then we have the gamma oil here multiplied. Okay, then we work around the U-tube. Not YouTube. We got around the U-tube here. This 0.1 and 0.2 are the same heights. So right pressure here technically is the same because same fluid and same height. So we just have to account for the rest here. H3. So now we're getting less deep, right? Maybe that's a better way of saying it. Sorry if I was confusing you guys earlier. But we're getting less deep. So that means the pressure is decreasing. I know I sound like a broken record, but if you get confused, the way I think about it, right, you're swimming. The deeper you go into the water, pressure increases. The higher you go back up when you're swimming, pressure... Sorry, I misspoke again. If you're ever confused and you just think about yourself swimming, if you're swimming downwards into the lower to the water, the pressure is increasing. If you're swimming upwards, the pressure is decreasing, right? So here we're going upwards now. The depth is getting less, so the pressure is decreasing minus. Okay, so now what we're also learning, there's an or, this is another equivalent statement. If you don't have the specific weight of the oil, you can use the specific gravity of the oil and you can multiply that by the specific weight of water. And that is equivalent to the specific weight of the oil. So you can see here they just substituted that specific gravity of oil times specific weight of water, equivalent to specific weight of oil. And same here for mercury. Okay, plug and chug. I'll let you experiment and do that. And here you get your answer in pound per foot squared. Convert that to PSI, and here's your answer. And a lot of times too, and just to save time, once we get these variables, just plug and chug. I will try to be prepared and just have the answer for you, because you all are probably pretty experts now at your calculators. So, okay, important thing to know from last example, like I said, you can use this if you can find your specific weight of your oil if you have the specific gravity of the oil and your specific weight of water. Okay, and then here, this is one of your homework problems. I guess this kind of gives it away, but it's already in the textbook. If there is an incline of the tube for a manometer, it's essentially the same idea, except the height you just have to calculate using your trigonometry. So here you have your pressure A, right? Start from left to right, like how I usually like to do. So pressure A, we're going down to this height. We are going lower in depth, so the pressure increases. So we add. So that's going to be gamma 1 H1. Okay, and then we look here. Looks like we're going less deep, so the pressure is less, so we're subtracting. So now we have gamma 2, and to get the height, it's just your trigonometry. This is the angle theta, so you have the opposite over hypotenuse, and so that's going to give you the height, right? So that's that part. And then here you're going higher again, less depth, so that means less pressure. Then you have your gamma 3 fluid times your height 3 here, all equal to pressure B. So this was kind of more directly from the textbook, and this is exactly how I was explaining my process earlier. So hopefully this clears it up for you. Okay, we're getting closer to the end here. I think we're around 32 minutes, so we're doing good. I'm going to try to keep this under an hour, because we might, like I said, do a chapter 3 lecture online as well. So hydrostatic forces on a plane surface. And let's just skip to the diagrams here. Maybe it'll be easier to explain. So this is just looking at surfaces submerged underwater. And we are looking at the pressures and forces applied depending where that interface is. So here on the left, this is just your normal tank. We have the free surface where pressure is 0. We're setting it 0 here. And you can usually do that with the majority of your problems, right? Pressure is 0. And you have your free surface here. And this is the pressure on the tank at the bottom. And you can see it's uniform here, which kind of makes sense. And this kind of only works for static fluid problems though, right? No shear stress. Here in the diagram to the right, we have you can see the pressures on the side of the tank is not uniform. It increases as you get lower in depth, which is exactly kind of been the whole idea of this lecture, right? So let's go to our bullet points now that we explained the diagram. Pressure at the bottom of the tank is uniform. Just talked about that. Pressure at the end varies linearly. It's right, yeah, this varies linearly here. It's harder to find a force resultant. Forces are always perpendicular to the surface since fluid is static, which we talked about really early in the lecture, right? Where these forces are perpendicular to the areas they're getting applied to. So the goal is to understand equations for hydrostatic forces and the location of where the force resultants are going to be for these submerged plates. So we're going to go deep dive into how the equations are kind of derived. And I actually do remember when I took this class, this was kind of a thing I remembered for some reason. So we're just gonna try to understand this diagram on the left here, right? I always like to look at diagrams first before getting into the reading. Makes the reading of the bullet points easier. So here you have your water. This is the free surface, or I guess any liquid. Here is a submerged plate. And the reason why we have this, because the whole point, right, is to find these hydrostatic forces on a submerged plate. And here, you see it's at an angle, right? It's not just a flat plate like this. That's look like this, this figure A here, because that would be too easy, right? We want it more difficult if it's like angled this way. So here we have the surface, right? And then this is the plate. And this view here, right? This is just looking when you're looking into the plate. It's just an arbitrary shape. So that's why they made it into this like this blob-looking thing. And you can look into the textbook. They use a lot of integrals in their and parallel axis theorems for this. So it accounts for any shape that you happen to make for your submerged piece of material, I guess, right? Okay, so here's a submerged plate. Looking into it is this view here. And now I believe we can probably get into these bullet points to kind of make sense now. So point O, which is up here, that's the point of the interface of the fluid and plate, which is this line here, right? Interface of fluid and plate intersects with the free surface, which is here. And that gives us this angle theta here. A is the area of the arbitrary shape, right, which is here. We don't know what shape it is. dA is a small infinitesimal or differential area on a shape. You probably hear that a lot in your multivariable calculus class. And then dF is a small differential of a force or infinitesimal of the force resultant, which is this dF here. Right, they're just relating it from this blob to here, to this view. C is the centroid of your arbitrary shape. CP is the center pressure location of the resultant force. And I'm going to note this later, but you can kind of see already that the force resultant is not applied at the centroid, right? It's applied at this location. It's different. And that's the whole reason why we're learning this, right? Because in a fluid, it's different because the pressures are increasing as you get lower in your fluid here. So FR here is the force resultant. The rest of the variables are just basically distances to everything I described before. So I'll let you look through that, your Y, YC, YR. You can pause the video here and you can kind of see where these are coming from. Okay, I just explained this diagram. If it's not clear, I recommend you pause, read through it, or rewatch because it's going to really affect the next slides here. Okay, so the equation for force resultant. The force resultant here, we're skipping to it just because it might be easier to understand, but they have more derivations in the textbook. It's just equal to the gamma specific weight times the height from the free surface to the centroid, right? We explained that back here. HC right there, times the area of where the force resultant is applied, area. Okay, here's a picture right here. So, and note the force resultant does not go through the centroid, right? Because we're under a fluid, the pressure is different at lower depths. So here's exactly what it is. Force resultant right here, away from the centroid. Here's the equation for force resultant. Okay. So now, trying to find the Y location of that force resultant. So you have your IXC here, which is your second moment of area, or your area moment of inertia. And you can see the derivations in the textbook if you'd like, and you'd review some parallel axis theorem. It's essentially the area moment of inertia with respect to an axis passing through its centroid, right there, and parallel to the x-axis. And then YC is the distance from the free surface to the centroid in the y direction. So right here. And A is the area of where the force resultant is applied. You'll see here, right? So you can do the integrals from your mechanics of materials class if it's a weird shape, but we have preset equations for these shapes that I'm going to show you in a bit, and I'm going to try to stick to those instead to make it a little bit easier for you. But you could always review those integrals just in case if you get a weird shape. The x location is pretty similar to the y location you can see here. Most of the homework problems and maybe things on and problems we'll get on exams, we're going to go for the y location here instead. But here the inertia here is the product of inertia, which is an asymmetric bending, which I noted here, compared to a symmetric bending here for the y location. And it's the product of inertia with respect to an orthogonal coordinate system passing through the centroid, which I showed earlier, right, of the area and formed by a translation of the xy coordinate system. So I didn't box this in red. Like I said, I don't know how often we're going to use this. We might just be good enough with using the y location based off the homework I saw when I reviewed it. But I wanted to provide this equation for you in case you needed it. YC is the distance from the free surface to the centroid in the y direction, and XC is the distance from the free surface to the centroid in the x direction. A is the area. And here is what I was talking about, right? Your area moment of inertias, right? So pretty nice here, right? So you have your normal rectangle, your circle, triangle. Instead of integrating, you have these set for you, right? The units are a dimension to the fourth power, which you should already know from your mechanics of materials class. Okay, we're going to jump into an example here and see how these equations work. So here, kind of similar to the diagram I explained to you earlier, we have a 4-meter diameter circular gate, right? And it's not just flat, right? It's at an angle. And it's located on an inclined wall of a large reservoir containing water, this is the specific weight, right? Newtons over meters cubed. The gate is mounted on a shaft along its horizontal diameter, and the water depth, that's going to be the depth from the free surface to, looks like the centroid here. Yeah, because it's right there, is 10 meters above the shaft. So we're going to determine the magnitude and location of the force resultant exerted on the gate by the water. Okay, so we already had the equations we derived before, right? So force resultant, we have our specific weight already given here for the water. HC is 10 because that's the distance from the surface water to the center of the gate here. And then area is the area of this gate, which is circle is pi r squared, right? So pi r, diameter is 4. So the radius of that is 2. So 2 squared is just 4. So then, yep, right here you get 4 pi. Nice and easy. And again, sorry that it's already kind of out here already. In class, I would do these for you live as a demonstration. But I just thought it'd be more clear here on the screen rather than using my bad video camera here and writing on paper or a whiteboard. Okay, so we have the force resultant, and now we need to locate the point center of pressure, which the force resultant acts upon. So these were the other two equations that we wrote, right? So here already, look, we see that this XR is not used. I'm not saying we're not going to use it, but your homework and this example in the textbooks don't really use XR as often since the area is symmetrical. So XR is going to be 0 here. The center pressure must lie along the diameter AA. So now we're going to find the YR, right? So the area moment of inertia for a circle, lucky us, we don't need to integrate. So we get to skip some Calc 2, which I don't know who's a fan of Calc 2, but that was one of my harder calc classes for me at least. So here we have pi r to the 4th power divided by 4. That's the area moment of inertia. YC, right? We have all we have YC. Where is YC? Nope. YC is right here. It's 10 meters divided by sine of 60 degrees. That's just trigonometry here for this angle. And then you have the area, right? Same as before, 4 pi. And then YC, again, is here. And you do all the math, computing, you get 11.6 meters. And the distance along the gate below the shaft to the center of the pressure, you have YR minus YC, right? So it's basically your YR is the distance for the resultant, and then YC is the distance right here, shown right there. And this is the distance from the centroid to the force resultant, because that's the difference right there. Right, and here again, look, here's another key concept. If I were to do a key concept question, this would be pretty good, right? For hydrostatic questions, if the plate is not fully flat and level, the force resultant does not go through the centroid because the pressure is increasing as we go deeper into the water. Okay, we made it to the end. Here are some of the equations at the end of the chapter. We basically went through this 2.4, 2.7, 2.18, 2.19, 2.2. And here are other ones, but I don't think these are on your homework. But here they are, just in case if you do the rest of the readings. Okay, we're going to get through some administrative stuff now. We're at about 46 minutes. Okay, we're trying to keep it under an hour. We're doing okay. And like I said, sorry that I'm not feeling too well. So if I'm thinking a little bit slow here or my voice is not good, please bear with me and feel free to ask me any questions if nothing's clear, because I really want you guys to get this content. Okay, so quiz information. I found out that, we'll just leave it outside of presentation mode here, that section B is having their quizzes in person. So I thought it'd only be fair if we matched them as well. I was contemplating about doing them online because it might take too much lecture time up. So I might just try to keep them short, under 15 minutes, or maybe 15 to 30 minutes. So under 30 minutes for sure. Maybe aim around 20 minutes. So someone asked about an equation sheet. I made an announcement, but just stating it here. You're allowed an equation sheet, but only one side of half a sheet of paper. I was going to do an index card, but I was like, there's different index sizes. Let's just make it easy. Do half a sheet. You will not be allowed to write any example or homework problems on your equation sheet. I don't want you to just write the homework and copy it and then have it ready side by side, right? I still want you to problem solve from what you learned. So you're only basically allowed equations in your equation sheet, maybe some units if you need it, some constants. If there are constants, I'm going to probably provide them for you. And I'm going to look at each equation sheet before we start the quiz. And if there's any discrepancies, you won't be able to use that equation sheet for the quiz. So just, like I said, no written examples, right? Just the equations that you might need. So like, stuff like this. All right, can write units. We already talked about that. I'll make another announcement when you get closer to quiz time once I write it. Yeah, it will probably not take longer than 20 minutes. So like I said, it will be in between 15 to 30, but probably no longer than 20 minutes. I'll give you a lot more info when I write it and we are there in person. Quiz problems will have the same topics as homework. So I wouldn't totally bank on having the same exact problems, right? It could be kind of similar, so you still problem solve, but I'm trying to make it easy that if you understand the homework, you should understand the quiz. And the quiz will have to be done at the end of the class. And I wanted to do it at the beginning, but for like administrative purposes, we're going to do it at the end. So I'll probably give you a break when lecture is over, and then we'll go do the quiz right at the end. Okay. Office hours. I posted a survey on announcements. You can, let's go to Canvas here. If you go to announcements, this announcement here, you can see I posted a when to meet. I could have just made my own hours, but I thought I would want to pick a time that's working for you, everybody. So I don't want a time just works for me. And yeah, so this looks like thanks when people are already filling these out. Awesome. So yeah, keep filling that out, and then I'll set some office hours. I'll always stick around after class for some questions if there are. I do have to head to work right after class to Boeing, so can't stick along too long, but I will try to stick around as long as I can. And another thing as well, another resource for help is the QSC, which is the tutoring center at Bothell. For those of you who don't know, the tutor there is Baoming, and I believe Baoming may be the only one that is able to tutor this class. Baoming is awesome. Baoming actually helped me with some classes when I was in undergrad here at Bothell. So yeah, I would suggest getting help from Baoming if you need some help from the class, or like I said, I'll have office hours or emails, or you can schedule appointments with me. Just send me an email. And here are, you can look at the QFC website, but from what I got, Baoming is available Monday, Wednesday, 10 a.m. to 2 p.m. or Fridays, 11 to 3. Okay. I don't want to keep everyone too long. I think there's one last slide here. I was posting homework hints of which sections to which problems. This one, it looks like you should be able to just basically use whatever is what we talked about today and do it from question 6 to the rest of the homework. And you should have enough content or lecture content now to finish the whole homework 1, which the quiz will be about on Monday, just homework 1. And like I said, homework 1 will not be collected, right? The ones, because there's already posted solutions. Your homework grade will be based on the quiz. Okay, let's see how long we went here. Okay, under an hour. I'll take it, under an hour. Awesome. So that's not too bad, right? Because I let you guys out a little bit early on the first lecture, and then we missed Wednesday, so we had this. So we probably have an hour left, technically, for lecture time. So I'll have one more 1-hour lecture that kind of gives an intro to chapter 3 and some concepts. And then once we come back on Monday, we're going to dive more into chapter 3 so we stay on schedule so we can get all of the fun learning for fluids. Okay, I'm going to end it here. Thanks, everyone, for watching. Sorry again that I don't feel well and my voice is bad and I'm kind of off my game today, but tried my best so we can stay on schedule for everything we have to do this quarter. We're going to be really busy. Okay, I hope you all have a good rest of your week, a good weekend, and feel free to email me with any questions. All right, bye.